I am JCastro, chemist from Tech in Ecuador. I am very pleased to present you Chem, a new geometric approach for porous materials with symmetric porosities. Porous materials are 3D networks of atoms ordered so that they form arrays of uniformly sized cavities with molecular dimensions. Due to their novel and enhanced capabilities, the interest in the studies of porous molecular materials has been increasing. The computational modeling of this system has allowed obtaining real and precise descriptions of their basic parameters such as size and shape of their porosities. However, computational studies of these materials face two main problems. The first one is related with calculation method limitations. DFT and basically every ab initio method are inherently limited to systems with a small number of atoms. In addition, the current geometric model is based on the polyhedrons that can be formed by using the metal atoms as vertices. This is a good approach for the shape of the molecular frameworks, but it fails to represent the internal surfaces where relevant applications actually take place. In this context, Chem is both a method and a software designed to provide a new approach to porosity for highly symmetric porous materials. The ordered arrays of atoms linking the pore walls can be thought of as defining a surface internal to the solid. The Python-written algorithm of Chem determines the atoms in the structure of a material that actually contribute to form the internal surfaces. Then it selects the convex uniform polyhedra that best resemble the shape of the porosities. It takes advantage of the symmetry present in these materials to generate a minimal volume element where high-level quantum mechanical methods can be applied rigorously, allowing the achievement of high-precision results with a significantly reduced computational cost. Original methods, open source codes, and several algebraic and geometric operations are coordinately executed by Chem through the use of its four main routines: legando, kerno, mosaico, and fragmento. The unitary cell of mode number 5 is used here to illustrate these procedures. The Chem's execution goes as follows. Leganto is the simplest and shortest of the four main routines. It is called first for reading the input XYZ file containing the structure of a material and transforming the information to an adequate format for further routines. For this purpose, Leganto makes use of regular expressions and Python dictionaries. Kerno is more interesting. It is itself a robust algorithm for finding the centers of a porosity in any porous structure through the analysis of the pore size distribution function of the material and a series of filters and grouping of closest candidates. However, its most remarkable function is to determine the atoms that contribute to form the internal surface of the cavities. That is why Kerno is the keystone of Chem's execution. In Mosaico, the contributing atoms previously selected by Kerno are used as vertices in a well-known computer graphics operation called Delaunay triangulation to generate limiting meshes for the surface of the porosities. Further processes in Chem require the triangulated surface of the convex fluid to be transformed into the polygonal faces of a polyhedron. For this task, Mosaico classifies the triangle according to which of them lie on the same plane to form polygonal faces. At the end of this polygonalization process, the convex fluid of the triangulation is transformed into a regular polyhedron whose volume, surface area, and number of faces are known. Fragmento is the final stage in Chem. Here, the shape of the polytope generated by Mosaico is compared with that of different regular polyhedra, Platonic and Archimedean, and that polyhedron, whose shape best resembles that of the polytope, is used to model the porosity. Once the fitted polyhedrons are properly aligned with the porosities of the material, the reverse wave construction procedure can be used to obtain the generating or Schwarz triangle of the selected fitted polyhedron. And from this, the irreducible volume that contains all the relevant sides of the pore modeled with the fitted polyhedron is generated. Of course, a proposal wouldn't be complete without an application example. The goal here is to find the position of the adsorption sites for small non-polarizable molecules, like helium, inside the porosities of mode number 5. Before calculating any properties, the most stable structure should be found. The optimization process starts from an initial structure and should converge to a minimum. It means that the input of any software requires an initial guess and a starting structure. In the adsorption context, it could be done with chemical intuition, but this method will be too inefficient for large systems. So the question here is how to choose the starting position closer to the real adsorption site in a systematic manner. Well, we found that upon geometrical optimization, the critical points provided by Chem are indeed very close to energy minima, so that they are very good approximations to real adsorption sites. It serves as proof that the implementation of this method greatly simplifies the process of determining the position of absorption sites in symmetric porous materials. After that, we can conclude that Chem provides a more realistic representation of the particularities of the interior of the porosities while allowing the generation of an irreducible volume where quantum mechanical effort can be focused. It is generic, so this process can be generalized for a wide variety of porous material. DeltaChem helps to find the absorption sites in an elegant manner. Preliminary results show that the site of the absorption can be found with an error of around 0.5 angstroms. The design of the program makes accessible all the information regarding the geometric analysis of the materials. DeltaChem will be improved, but takes less than 1 hour to give satisfactory results. The program, of course, is still under development and more studies are required, but first results are promissory. DeltaChem approach and the software itself are the result of a highly interdisciplinary work at the boundary between geometry and chemistry. They are an example of how mathematical tools and computational methods can be used to simplify and overcome chemical issues. Thanks for your attention.